Alright, non-resident training course, September 1998. Navy Electricity Electronic Training Series, Module 11, Microwave Principles, Navy NAVED TRA 14181, sorry, NAVED TRA 14183. Distribution Public Statement A, approved public release distribution unlimited. Table of Contents, Chapter 1, Waveguide Theory Application, Chapter 2, Microwave Components and Circuits, Chapter 3, Microwave Antennas. Alright, throughout this text over the course, you will use the technical manuals associated with the equipment you will be working on. You will find the below notations and some of the paragraphs notations are used to emphasize the safety hazards exist and care must be taken and observed. Warning, an operating procedure, practice, or condition, etc., which may result with the injury or death if not carefully observed or followed. Caution, an operating procedure, practice, condition, etc., which may result with the damage of equipment if not carefully observed or followed. No, an operation procedure, practice, condition, etc., which is essential to emphasize. Alright, Chapter 1, Waveguide Theory and Application. Learning objective. The use of upon completion of the chapter, this student will be able to describe the development of various types of the waveguides in terms of the advantages and disadvantages, describe physical dimension, various types of waveguides, explain their effects on those dimensions of the power and frequency. Explain the propagation of energy waveguides in terms of the electromagnetic field theory, identify the modes of the operation waveguides, explain the basic input-output methods of using waveguides, describe the basic principle of waveguide plumbing, examine the reason for the method of terminating waveguides, explain the basic theory of operation and application for the directional couplers, basic theory of operation construction, application of cavity resonators, describe the basic theory of operation waveguide junctions, explain the operation of ferrite devices in terms of their application. Introduction to waveguide application theory. The portion of the electromagnetic spectrum which falls between 1,000 MHz and 100,000 MHz is followed as a microwave region. Because of the discussing the principal application of the microwave frequency and the mean of the determined microwave G of the module must be established on the strip. The definition of the microwave would appear to be simple because of the electronics to prefer to micro normally means the millionth of part of the unit. Micro also means small, which in relatively term U of the center of the module. Microwave term loose is applied with the identified electromagnetic waves of 1,000 MHz in frequency with it because of the short physical wavelength of the frequency, short length wave energy offer the distinct advantage they may with the application. For instance, excellent directivity can be obtained with a using relatively small antenna, lower power transmitter. These features are ideal for both military, civilian, radar communication applications, such as small antennas and other small components that are made possible by microwave frequency application. It is important to consider shipboard equipment, the handling of the where space and weight are more major problems. Microwave frequency use is especially important in the design of shipboard radar because it makes possible the detection of smaller targets. Microwave frequency presents special problems with transmission generated with the circuit design that are not encountered with lower frequencies. Conventional circuit theories are based on voltage and currents, while microwave theory is based on electromagnetic fields. The concept of the electromagnetic interaction is not entirely new, since electromagnetic field form is basis of all antenna theory. However, many student electronics find electromagnetic field theory very difficult to visualize and understand. The module will present principle and microwave theory in its simplest terms possible, but many of the concepts are still somewhat difficult to thoroughly understand. Therefore, you must realize this module will require very careful study for you to properly understand microwave theory. Antenna fundamentals will cover the Neets Module 10, Introduction, Wave Propagation, Transmission Lines, and Antennas. This module will show you the solutions properly encountered with microwave frequencies, beginning with the transmission microwave energy, continuing with through waveguides in Chapter 1. Later chapter will cover the theory of operation, microcomponents, and circuits and antennas. The application of these concepts will discuss more thoroughly in later Needs modules on radar and communications. Waveguide theory. Two-wire transmission line is conventional circuit that is efficiency of transferring electromagnetic energy into microwave frequencies. At these frequencies, energy escaped by radiation because of the field that are not confined in all directions are illustrated in Figure 1.1. Coaxial lines are more efficient than two-wire lines for transferring electromagnetic energy because the fields are completely confined by the conductors illustrated in Figure 1.2. 1.1 show the fields confined in two-directional only. The fields not confined in this direction. Fields are confined in this direction. Okay. Your end-view coaxial cable fields are confined in all directions. Waveguides are most efficient way waveguides are the most efficient way to transfer electromagnetic energy. Waveguides are essential coaxial lines without concentric conductors. They are constructed with a conductive material with a rectangular, circular, and elliptical shape shown in Figure 1-3. Circular, elliptical, and rectangular. Waveguide advantages. Waveguides have several advantages. Two-wire coaxial transmission line, for example, the large surface area of the waveguides greatly reduced the copper amperes are squared over the arms with losses. Two-wire transmission line that have a large copper loss because of their relatively small surface area. The surface area of the outer conductor of the coaxial cable is large, but the surface of the inner conductor is relatively small. At microwave frequency, the current carrying area of the inductor conductor is very restricted and very small layer of the whole surface of the conductor by action called skin effect. Skin effect is discussed in Neets Module 10, Introduction Wave Propagation Transmission Line with the Antennas. Chapter 3, Skin effect tends to increase the efficiency resistance of the conductor. Although the energy transfers and the coaxial cable is coupled with the electromagnetic field motion, the magnetic magnitude of the fields is limited inside of the current carrying area of the inductor conductor. The small side of the center conductor is further reduced by skinning effect energy transmission by coaxial cable because less efficiency than by waveguides. Directional loss is also lower with the waveguides than in two-wire coaxial transmission lines. Dielectrical loss in two-wire and coaxial lines are caused by heating of the insulation between the conductors. Insulation behaves as a dielectrical capacitor formed with the two wires. The transmission line of voltage potential covered the two wires caused by the heating of the dielectrical result of the power loss. Practical application of actual breakdown of the insulation between the conductors. Transmission line is more frequently the problem than dielectrical loss. The breakdown is usually caused by the stationary voltage spikes or nodes, which are caused by the standing wave. The standing wave is a stationary occur where part of the energy traveling down the line is reflected by impedance mismatch with the load and the voltage potential of the standing wave at the points of the greatest magnitude become large enough to break down the insulation before the transmission line conductors. The dielectrical waveguides is air. The dielectric is in waveguides is air, which has more and lower electrical loss than conventional insulation material. However, the waveguides are also subject to dielectrical breakdown caused by a standing wave. The standing waves are waveguides causing arcing which decrease the efficiency of the energy transfer with a considerably severely damage the waveguide. Also, since the electromagnetic fields are completely contained within the waveguide, radiation loss are kept very low. Alright, power and capability is another advantage for the waveguide. Waveguides can handle more power with the coaxial line same side of the because of the power handling capabilities directly related to the distance between the conductor. Figure 1-4 illustrates the greatest distance between the conductors in a waveguide. Alright, you have S1 and S2 spacing in S1 and S2 conductors, coaxial cable, circular waveguide. In the view advantage of the waveguides, you would think that the waveguide should be only type of the transmission line used. However, the waveguides have certain disadvantages that make them practical for use only at microwave frequencies. Waveguide disadvantage: physical side of the primary lower frequency limitation of the waveguide. The width of the waveguide must be approximately half of the wavelength of the frequency of the wave to be transported. For example, the waveguide uses at 1 megahertz that would be about 500 feet. This makes the waveguide at frequencies below 100,000 megahertz increase impractical. The lower frequency range of any system using the waveguide is limited by a physical dimension for the waveguides. Waveguides are typically installed to give the grid of the hollow pipe shape of the special couplings at the joint are required to ensure the proper operation. And also, inside of the strip of the waveguides are often played with silver and gold to reduce skin effect loss. These requirements increase the cost and decrease the practicability of the waveguide system and any other microwave frequencies. Developing waveguide parallel lines. You may better understand the nutrition of the ordinary transmission line with the concept of the waveguide theory for the consider the development of the waveguide of the two-wire transmission line. Figure 1-5 shows the section of the two-wire transmission line supported on two insulators. A junction within the line of the insulator must be present with a very high impedance to ground the proper operation of the line. A low impedance of the insulator would be obviously the short circuit line ground that was not what happens to be very high frequency. Ordinary insulators display with the character of the dielectrical of the capacitor formed by the wire of the ground. As the frequency increases, the overall impedance decrease the better high frequency insulator with the core wave section of the transmission line is shorted at one end. Such insulators as shown in Figure 1-6. Impedance of short core wave section is very high at the open end of the junction with the two-wire transmission line. The type of the insulator is known as the metallic insulator may be placed anywhere along the two-wire line. Note that the quarter wave sections are insulators at only one frequency. The several limits of the bandwidth efficiency and application of the type of two-wire line. Alright, figure 1-5 show the two-wire transmission line using ordinary insulators, and also show the quarter wave section transmission line shorted at one end, two-wire transmission junction short circuit. Figure 1-7 show the several metallic insulator at the end each side of the two-wire transmission line. As more insulators are added, each section makes contact with the next. If the regular rectangular wave guide is formed, the lines become part of the walls of the waveguide. As illustrated in figure 1-8, the energy is then conducted by the hollow waveguide instead of the two-wire transmission line. Figure 1-7, there was metallic insulator with each side of the two-wire line. Also, figure 1-8 shows the forming of a waveguide adding quarter wave sections. Okay. The comparison of the wave of the electromagnetic field with the transmission line of the waveguide is not exact. During the exact change of the two-wire of the line with the waveguide, the electromagnetic field configuration undergo many changes, which will be discussed later in the chapter. As a result of these changes, the waveguides do not accurately operate with a two-wire line as completely shown with the quarter wave section. If you use the waveguide, would be limited to a single frequency wavelength that was 4 times the length of the quarter wave section. In fact, the waves of the length cannot pass efficiently through the waveguides. Only a small range of frequencies, a somewhat shorter wavelength, at higher frequencies can pass efficiently. As shown in figure 1-9, the wide dimension waveguide is called A dimension that determines the range of the operating frequency. The narrowest dimension that determines the power handling capability of the waveguide is called the B dimension. Alright, so your A dimension show the determine the range of the operating frequency. Your B dimension is the power handling. Waveguide 1, waveguide 2. Alright, note, the method of labeling waveguides is not standard in all texts. Different methods may be used in other texts of the microwave principles, but methods according to the Navy military standards are MLISTDS. The ability of the waving guide to give the dimension to transport with one frequency may be better with the understanding analyzing action illustrated figure 110A, B, and C. A, the waveguide may be considered to have an upper-lower quarter wave section, central section, which is over the conductor called the bus bar. In figure 110A, the distance of the MN is equal to the distance of PU, but both are equal in 1/4 wavelength. 110 frequency effect of the waveguide normally operating frequency. Note, throughout the Neets for the 1/4 and wavelength of the fourth and quarters are both represented in 1/4 wavelength. They are usually interchangeable. Also, wavelength under 2 and 3 halves of wavelength will be represented with a 1/2 wavelength and 1 1/2 length respectively. Distance for the non-positive is the width of the bus bar, the overall dimension for the waveguide held and constant required with the length of the quarter wave section of the decrease of the frequency and increase of the illustrated of the figure 110 with the cup with the width of the bus bar with the increase of the theory of the waveguide could function with an infinite number of the frequencies higher than the desired frequency is larger. Length of each of the quarter wave sections approaches the zero of the bus bar continually to widen the field of the available spaces. However, in practice, the upper frequency limit is governed by modes of operation, which will be discussed later. All right, increasing frequency, NPQ, quarter frequency of the effects of the waveguide, increasing frequency, and frequency effect of the wave, decreasing frequency, quarter inch waveguide. And the frequency signal is desired is so much for the 2/4 wavelength, as long as are longer with the wide dimension of the waveguide, energy no longer pass through the waveguide. The lower the frequency and limit of the cutoff frequency of the given waveguide. In practical application, wide dimension of the waveguide is usually 0.7 the wavelength of the operating frequency. This allows the waveguide handle a small range frequency both above and below the frequency operating frequency. The B dimension is governed by the breakdown potential of the dielectrical, which usually in the air. The dimensions range from 0.2 to 0.5. Wavelength commonly with the B side of the waveguide. Energy propagation and waveguides. Since every energy is transformed by the waveguide by the electromagnetic fields, you need the basic understanding of the field theory. The magnetic theory, H field, the electrical field, the E field, are present in the waveguide with the interaction with these fields. Call for the energy to travel through the waveguide. This action best understood first looking with the property to individual field. The electrical field exists the difference of potential call for the strength of the dielectrical between 2 points. The simplest electrical field is one of the forms between the plate of the capacitor. One of the plate is made positive compared to the other, as shown in figure 111. Stress is created with the dielectrical and an electrical field. The electrical field is represented with the arrow points of the positive toward negative potential. For the number of the arrows show the relative strength of the field. Figure 111A. For example, the evenly spaced arrows indicate that the field is evenly distributed. For easy explanation, the electrical field is abbreviated as the E field. Lines of stress are called the E lines. The 111 shows a simple electrical field's capacitor. Figure 11B shows a simple electric 2-wire transmission line. Generator, 2-wire transmission line. Instantaneous standing value, 2-wire line. 2-wire transmission line illustrated in figure 111B with a heads instantaneous standing wave value. Wave of the voltage applied to its generator. The line short of the circuit with the one-way wavelength of the high with the negative voltage. People, the arrows represented each of the field with the pointing in the opposite direction. The voltage across the lines vary. sinusoidal. Therefore, the density of the electromagnetic field of the lines are varies. The electric field lines vary sinusoidal. Development of the electric field of the waveguide can be illustrated with the two-wire transmission separately with the several double quarter wave called the half wave frame. For the illustrated figure 112 is shown with the voltage of the two-wire lines vary with the same wave pattern of density of the electrical field, but they also vary with the same wave pattern with the half wave of the frames force with the high voltage 1 and 3 with have the strong electrical field of the frame 0.02 have no electrical field present with the frame 4 with the weaks of the electrical field located at the point of the maximum minimal voltage illustrated build up the three-dimensional aspect of the full field electrical field and waveguide. Generator half wave frame strong frame half wave frames removed from the main line. The electrical field standing wave no electrical field stand 3 two-wire line short electrical field weak. Figure 113 view A show with the electrical field pattern with the created with the voltage sim wave applied with the one wavelength section with the waveguide shorted at one end. The electrical fields are represented with the arrow shown with the view BC. Top of the view A with the tip of each of the arrow represented with the dot and tail of each of the arrow represented with the X. Each the electric field vary with the density with the same wave with the rate with the applied with the voltage. The illustration represents the instant of the applied voltage wave as it peaks. The other time of the voltage electrical field of the waveguide variously continue with the zero to peak value of the voltage electrical field polarity reverses with every reversal in of the input. Note that the end view is shown with the view with the B with the show of the electrical field with the maximum center minimum near the wall of the waveguide view with the C with the show of the arrangement electromagnetic field of the three-dimensional waveguide. Voltage standing wave at end view dimension A dimension dimension A view wave two wave. The B dimension side wave lengthwise top three-dimensional view. The magnetic field, H field. The magnetic field is wave made over the magnetic lines for the cover of the current flow through the conductive material of the wavelength. The magnetic lines of force are called the H lines. Continuous closed loops are shown in the figure 114. All of the H lines are associated with the current or collective magnetic field. Their H field. The strength of the magnetic field is indicated with the number of the H lines in the given area vary directly with the amount of the current. Figure 114 shows the magnetic field of the single wire electrical field. Although the H lines encircle the single with a straight wire, they have differently with the wire formed with the into of the coil shown in figure 115. In a coil, the individual H lines tend to form around each of the turn of the wire. Since the H lines go opposite direction between adjacent terms of the field between the turns and cancel inside and out of the coil, where the direction of the H field magnetic field is the same as the field joins and forms the continuous magnetic field lines around the entire coil. Alright, figure 4 and 15 show the magnetic field on the coil lines of force from the individual turns join on with the forms of continuous magnetic field around the whole coil. The magnetic field of the cancel between the turns. As similar action takes place with the waveguide figure 116 with the two-wire line with a quarter wave section shown with the current flow of the main line with a quarter wave section. The current direction produced the individual magnetic lines around each of the conductors shown in the larger number. The section of the field cancels between the section both directions, same both sides, inside and outside of the waveguide. Half of the intervals on the main of the current will flow in the opposite direction. Produce the magnetic line loops out of the opposite direction. Figure 116 current with the left end of the opposite, but the current of the higher with the right end individual loops main line with the opposite direction all around with the framework is that they were joined long in the loop. Each figure in 116 formed outside of the waveguide. The individual loops cannot join with a continuous loop. No magnetic field exists outside of the waveguide. Figure 116 shows the magnetic of the two-wire line half-wave frames. The current is reversed every half-wave resistant distance from the circuit. The complete loop addition, but combining individual magnetic field of the current. 116 magnetic field, the two-wire lines of the half-wave frames. The two-wire line half-wave frames are developed in the waveguide clove at the both ends of the shown figure 116. Distribution of the H will be shown in the figure 117. Waveguide extended 1 1/2 and wavelength. These magnetic field with the complete the half loop, complete the loops at half-wave intervals, each with a group of the reverse direction, and no magnetic lines can force outside waveguide as long as it's completely enclosed. Show the 117 magnetic field pattern of waveguide A, B, C, D. Magnetic lines field with their maximum density along the imaginary planes of the A, B, and C, and D. Figure 118 shows the cross-sectional view of the magnetic field with the pattern with the figure 117 over the view A. The field is wrong with the edge of the waveguide with the current type of the minimum field strength with the curve with the 0 point of the view B with the show of the field pattern and theory for the quarter length. Wavelengths and quarters of the end of the waveguide. The opposite previous is go for the electrical field and the magnetic field shown in the figure 116, 117, and 18 are conditions exist that only one instance at a time. That during the peak of the next cycle, they have the input current. The all field directions are reverse field will continue to change with the changes in input. All right, top view A view with the A dimension with the weak field with the strong magnetic field half length. Cross-sectional view with the two end from the end view with the boundary condition of the waveguide. The travel over the energy down to the waveguide is similar but not identical to the electrical magnetic wave. In the free wave, the difference of the energy waveguide that's going on physical like the guide, the conditions, known the boundary conditions must be satisfied by the engineer. Energy to travel through the waveguide. The first boundary condition, the figure 119, can be stated as follow the electrical field that exists at the surface of the conductor perpendicular to the conductor. Electrical field with the electrical field boundary meets with the boundary of the condition. The opposite of the boundary condition shown in figure 119b, but also the electrical field cannot be exist parallel to the perfect conductor. Electric field with the boundary does not meet the boundary condition. The secondary boundary condition illustrated in figure 120 can be stated as follows. The very magnetic field that exists that must be closed with the loop is in parallel. The conductors be perpendicular with electrical field. Magnetic field, electrical field, and magnetic field dash from electrical field full lines. Since the electric field with the current flow for the term of the produce of the magnetic field, both of the fields always exist at the same time with the waveguide. At the time, since the system is satisfied with the other basic condition that it must also satisfy the other since the need field can exist alone. You should briefly review the principle of electromagnetic propagation for save the needs of the module 10 introduction wave propagation transmission line with an antenna. This review will help you understand the waveguide is satisfied with the two boundary conditions necessary to energize the propagation of the waveguide. Wavefronts within the waveguide. Electromagnetic energy transmitted in space exists electric and a magnetic field with a right angle with each other, the right with the angle with the direction of the propagation. Single angle analogy with establish the relationship to the right hand rule with the electromagnetic energy and the based on the pointing vector indicates a screw with the right hand thread with the axis of the perpendicular electromagnetic field to advance in the direction propagation of the field is rotated with the right toward the magnetic field. This rule is illustrated in figure 121. Show the pointing vector, the direction of propagation, middle finger of the E, the electric field with the thumb, the direction of the rotation, and the magnetic field, the index finger. The combination of electric magnetic fields form the wavefront with the representative of the alternate negative peak of the half wavelength intervals illustrated in 122. Angle 0 is the direction of the travel of the wave that respect to the sum of the reference axis. Direction of the travel reference axis, wavefront in space. Second, wavefront differing from only the direction of the travel, but at the same time result with the two is formed with the result in the illustrated figure 123 with the close inspection reveals the important character combined with the wavefronts. Both wavefronts at all points of the reference exist to cancel with a half wave the interval wavelength intervals with a reference axis. Therefore, all alternate additions or cancellation of two wavefronts occur with the progressive half wavelength increments of the reference axis. In figure 123, lines A, C, F, and H are additional points, and the labeled B, D, and G are cancellation points. All right, it was B, D, E, and G. The middle points are cancellation, and these are the additional points of the combined waveforms. Two conductor plates are placed along with the cancellation line with the D and the E with the cancel of the lines of B and G. With the first boundary condition for the waveguide will be satisfied that is the electrical field will be 0 with the surface of the conductor plate. For the secondary boundary condition, therefore, automatically satisfied since the plates are for the same purpose as B dimension walls of the waveguide. A dimension can also be added without affecting the magnetic electrical fields. When a quarter wavelength of the probe is inserted with the waveguide with the supply with the microwave energy will act as a quarter wave vertical antenna. The positive and negative wavefronts will be added as shown with the figure 124. The portion of the wavefront traveling with the direction of the arrow C will rapidly decrease to 0 because it does not fulfill either the required boundary condition. The parts of the wavefront with the travel in the direction of the arrows A, B reflect the wall of the from reverse phase of the wavefront. The two wavefronts, those that follow the illustrated figure 125, note that the wavefronts cross down the center of the waveguide produce the same resonant field pattern as shown with figure 123. 124 shows the resonant radiation from the probe placed in the wavelength. Antenna A, B, and C. Wavefront traveling in direction X, wavefront traveling in direction Y. Wavelength, wall of the waveguide, wall of the waveguide. B, electrical field, wavefronts in the waveguide. All right, the reflection of a single front with a B wall with the waveguide shown with the 126 with the wavefront shown with the view A with a small particle with the B and C with the particle with the one strike with the wall with the bound with the act from the wall without losing velocity. The wall with a perfectly flat with the angle which strike with the wall known with the angle of the incident with the same with the angle of the refraction and or measured perpendicular waveguide surfaces. The inside of the after the particle 1 strike the wall, the particle 2 strike the wall is shown view B and view C reflect the same end of because all the particles are traveling at the same velocity of particle 1 and 2, they do not change the relative position respectively each of the therefore the reflected wave of the same shape of the original remaining particle is shown with the D, E, and F. The reflect of the same manner. The particles result with the reflected wave from the identical shape of the opposite polarity incident wave. Figure A shows the direction of the front, the angle of the incident, and then C would be shown an instant with a particle 1 strike the wall and particle 2 strike the wall is shown in view C reflects the same manner because of all the particles traveling in verticals 1 and 2 do not change relative position. And the remaining particles of D and E and F reflect the same manner. The process reflects the reflected wavefront identification. So what you got is C, and then you get a wavefront like D, E, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's changed its direction. Figure 127 and 127 B with each of the illustrate the direction of the propagation. Two different electromagnetic wavefront. The different frequencies be illustrated, be radiated with the waveguide by the probe. Note that only direction propagation indicated by the lines of the arrowhead wavefronts of the right over the angle of the direction of the propagation angle of the instant of the angle of the reflection of the wavefronts varies the type of the frequency input energy of the angle of the reflection are equal to the other each of the other with the waveguide with the cutoff frequency of the waveguide with the frequency that was cover the angle of the instant of the reflection of the 0 degree of the frequency below the cutoff frequency. The wave fronts will be reflected back forth across the guide and setting up the standing waves. No energy will be conducted down the waveguide. 127 of the different frequencies of the waveguide and the antenna. Different frequencies in the waveguide. The velocity of the propagation wave along with the waveguide with the left of the velocity of the free space with the speed of light. The lower of the velocity of the curve with the zigzag path of the taken from the wavelength of the forward path with the velocity of the wavefront with the waveguide with the group of the velocity is somewhat slower than the speed of light. With the group of the velocity of the energy waveguide to determine the reflection angle of the wavefront for the B wall. Reflection angle determines the frequency of the input energy of the base of the principle illustrated in figure 128, 128B, and 128C with the frequency and creep of the reflective angle, creep of the curve with the group of the velocity, the creep of the output. Also true can creep the frequency and increase of the group velocity. Figure 128 reflection of the angle of the various frequencies, low frequency, and reflection angle of the medium frequency, reflection of the angle of the high frequencies, and also waveguide modes in operation. The waveguide analyzed in the previous paragraph yields the electrical field configuration over the half-sim electrical distribution. The configuration mode and call the mode of the operation. Shown in the figure 129, recall the strength of the field to indicate with the space of the lines that is close. The closer of the lines are stronger than the field of the region of the maximum voltage field move continuously, and the waveguide and sim wave pattern to meet the boundary condition. The field must also be zero with the B walls. Half-sim field is only one of the many fields of the configuration mode that can either exist rectangular waveguide or full sim, but the fields can a full sim field can also exist with the rectangular waveguide because of the shown figure 130, but the field is zero with the B walls. Similar to 1 1/2 sim wave, the field can exist with the rectangular waveguide because of the field is almost at the boundary condition with the shown figure 131 field with a particular with a conducting surface with a touch of zero along the B walls. A show the half sin of the electric field distribution A and B wall, and then full sin electrical field distribution A wall and B wall. A and B wall 1 and 1/2 sin electrical field distribution. Or the magnetic field and generator the rectangular wave that performed with the closed loop of the parallel surface of the conductor strength of the magnetic field, the proportional electrical field with the figure 132 that illustrates the magnetic field pattern across the field has an electrical field distribution. The magnitude of the magnetic field varies with the sim wave pattern down with the center of the waveguide with the time phase at the end. The electrical field, the time phase means the peak of the magnetic lines over the electrical lines occur with the same instant of the time. Although not necessarily the same point over the length of the waveguide. Figure 132 magnetic field cover the half sim of the electric field. The electric field of the sim wave pattern also exists down with the center of the waveguide. Figure 133 view A with consider the two waveforms C and the D. Assume that the power of the 1 negative at point 2 of the waveforms come across the point 1 and 2 with each of the field maximum strength. At these points, the field combines the further increase of the strength of the action continuously because each of the wave also is followed by a replacement wave. The figure 133 view B illustrates the resonant sim wave configuration electrical field with the center of the waveguide. The figure is one over the many field with the pattern that can exist with the waveguide. Each of the configuration forms a separate move over the operation. The earliest mode to produce is called the dominant mode. Other modes with a different field of the configuration made it excellently may be caused deliberately. Alright, so A and B crisscrossing wavefronts of resonant electrical field. Or the dominant mode is the most efficient waveguides that normally designed only with the dominant mode will use to operate with the dominant mode. The waveguide must have the wide dimension of at least 1/2 the wavelength with the frequency of the B promulgated with the A dimension. Waveguide must be kept the minimum allowable value to ensure that only the dominant mode will be exhibited. In practice, the dimensions of 0 points of the wavelength. Other possible mode of the operation available to give the waveguide dimension dominant mode with the local for cost frequency, high frequency limit with the rectangular waveguide. The frequency with the A dimension becomes large enough to the operating of the motor higher than which the waveguide was in design. Waveguides may be designed to operate more in a mode other than dominant mode. Example of the Wilson configuration mode is shown in figure 134, 134B. A and B, the dimension of the waveguide is in figure of one wavelength long. You must ensure that two wire is 1/4 3/4 wavelength from one of the B walls, as shown in Figure 134A. The remaining distance for the B wall is 3/4 wavelength, 3/4 wavelength section of the same height and impedance of the corner wave section. Therefore, the two-wire line improperly insulated with the field configuration show the complete sim wave pattern across a dimension in Figure 134A. Waveguide operation with the other dominant mode. 134 B, where B waveguide operation with the dominant mode. Arrows are E lines, are electrical lines. X's and dots are magnetic lines. All right, your circular waveguide for the specific areas of the areas of the radio of the communication system show the rotating joint for the mechanical point of the antenna rotate with the Figure 135 illustrates the dominant mode of the circular waveguide with the cutoff of the wave of the game with the circular waveguide is 1.71 times the diameter of the waveguide. Since the A dimension for the rectangular waveguide is approximately 1/2 of the wavelength of the cutoff of the frequency of the diameter of the equivalent circular waveguide is 2 divided by 1.71, approximately 1.17 the time for the dimension of the rectangular width white waveguide. Directional propagation dots when the arrows point to the arrows are at all tails. All right, your mode number of the system. So far, the only most of the basic type of the electrical field, the magnetic field arrangement have been shown, and the more complicated arrangement often necessary to make possible coupling, insulation, and other type of the operation. The field arrangement of the various modes of the operation are divided in two categories: transverse electric and transverse magnetic field. Transverse electric, transverse and magnetic. In the transverse electric mode, the entire field is transverse plane with within the material perpendicular with the length of the waveguide, the direction of the energy travel part of the magnetic field with the power with the length of the axis. In transverse magnetic mode, the entire magnetic field of the transverse plane has no portion of the parallel the length of the axis. Since the transverse electric and transverse magnetic modes then subscript that are used to complete the description of the field path with the rectangular wave, the guide with the first subscript indicates the next number of the halfway patterns in the full 8-dimensional second subscript indicates the number of the halfway patterns in the B dimension. To dominate the dominant mode for the rectangular waveguides is shown in Figure 136 with the design designated as transverse electric because of the electric field that are perpendicular with the A wall. The full subscript is 1, since only 1/2 of the wave portion of the cuff of the A, there is no electrical field patterns across B dimensions. So the second subscript is 0 with the complete mode. The descriptive of the dominant mode for the rectangular waveguide is the transverse electric 110 subscript. The subsequent description waveguide operation text will assume the dominant transverse electric 1-0 mode unless the otherwise are noted. Dominant mode of the rectangular wavelength transverse electric 1-0 mode. A system used to identify the mode of the circular waveguide with the general classification of the transverse electric, transverse magnetic true with both circular with the rectangular waveguide, circular waveguide with the subscript with a different meaning with the first subscript that indicate the normal the full wave patterns around circumference with the waveguide, the second subscript that indicate the number of the halfway patterns for around the diameter. And if there's no circular waveguide with the Figure 137, the electrical field with the perpendicular length of the waveguide is within the electrical field lines parallel to the direction of the propagation. This must be classified as the transverse electric mode. The following with the electrical line pattern with the counterclockwise direction, starting at the top of the electrical line, go from 0 to the back, from positive tail of the arrows back to 0 through the maximum negative head of the arrow of the back through the 0 again. This is one full wave. The full subscript is 1 as the long diameter of the volt and the electrical lines are go through the maximum to 0 back to 0, making a halfway variation. The second subscript therefore is 1. The transverse electric 1-to-1 is a complete mode, descriptive and dominating mode with the circular waveguide with the saved mode, several modes that are possible, both circular and rectangular waveguides. Figure 138 illustrates several different modes that can be used with varying the mode of the numbering system. Figure transverse electric 1-to-1 circular dominant, transverse 1-to-1 show the pattern 1/2 pattern, 2/2 patterns. Transverse electric 2-to-0, 1 and 1/2, transverse 1-to-0. Dimensions the dimension being 1/2 pattern and a half pattern transverse magnetic 1-to-1, transverse magnetic 0-1, 1/2 pattern no pattern, 1/2 pattern radius 3 transverse 1-to-1. All right, waveguide input-output methods. Waveguide is explained with earlier in the chapter operates different with the ordinary transmission line, but therefore the special devices must be put in and put energy into the waveguide at one end, but remove it at the other. The 3 devices use the inject with the remove the energy waveguide with the probe loops and slots. Slots may also be called the apparatuses or windows. I previously discussed a small probe that is illustrated in the Previously discovered the small probe that insert with the waveguide supplied with the microwave energy. It acts with the quarter wave. The antenna, the current flow of the probe sets up the electrical field such that the one shown in figure 139. The electric lines detach themselves from the probe. The probe is then located with the point of the highest frequency electrical line set up with the electrical field with a considerable intensity. 139A, the probe coupling rectangular wave. Also, 139B, the probe connecting the coupling with the rectangular wavelength. The wavelength at 1/4. Rectangular waveguide, probe coupling at the rectangular waveguide. Also, large diameter probe, low power, large diameter, small diameter, high power. Broad bandwidth probes. Probe coupling rectangular waveguide. The most efficient place to locate with the probe is in the center of the wall with a parallel to the B wall with a 1/4 wavelength. The short end of the waveguide is shown with figure 139B, but the 139C. This point is which the electrical field maximum of the dominant node there. Therefore, the energy transfer over the coupling maximum at this point and over the quarter wavelength, the spacing of the frequency required to propagate the dominant mode. In many applications, the lesser degree of the energy transfer called the loose coupling is desired. The amount of the energy transfer can reduce the decreasing length of the probe, moving it out from the center of the electrical field board by shielding it. With the degree of the coupling must be varied, but frequently the probe is made retractable so the length can be easily changed. The size and shape of the probe to determine the frequency band of the power handling capability diameter of the probe, increase the bandwidth, increase the power probe similar to the shape of the doorknob, but the case for the capable of handling the more higher power large bandwidth, a conventional probe. The greater the power handling capability directly related increased surface area of the two examples of broadband with probes are illustrated in figure 139. If you remove the energy of the waveguide, simply the reversal of the injection process, using the same type of the probe. Another way to adjust and wave the injecting energy of the waveguide is by setting up the magnetic field of the waveguide. This can be accomplished by inserting the small loop of the carrier for the high current of the waveguide as shown in figure 140A. With the magnetic field builds up around the loop is expanding with the waveguide as shown in figure 140B. Frequency of the current of the loop within the bandwidth of the waveguide energy was transferred to the waveguide. For most efficient coupling of the waveguide loop is inserted one with several points where magnetic field will be strongest and the greatest strength. Four of these points are shown in figure 140C. 148 shows the loop coupling the rectangular guide with the coaxial cable in the loop. 140 shows the loop coupling with the rectangular wave, the magnetic field lines. Also 140 shows the loop coupling with the rectangular waveguide magnetic field possible loop location for loop. When less efficient coupling is desirable, you can rotate the move of the loop and circle a smaller number of the magnetic line with the diameter of the loop. That increase the power handling and capability. Also increase the bandwidth of it. Increase the size of the wire with the used to make the loop. The loop is introduced into the waveguide and head of the magnetic field. It is present the current is induced at the loop. When the conditions exist, the energy is moved from the waveguide. Slots and wrappers sometimes were used when they vary loop for the coupling. If inefficient coupling is desired, shown with the figure 141, the method of the energy that through the small slot of the waveguide and the electrical field expanded into the waveguide. The electrical field expanded the first across of the slot and the cross of the interior of the waveguide. The minimum reflection of the curve of the energy of the injected removed the side of the slot. The properly proportioned frequency of the energy window of the slot of the apparatus. The slot of the coupling of the waveguide. After how energy is coupled in and out of the waveguide slot, you may think of the leaving the end of the most simple way of the injecting remove the energy of the wave in a waveguide. This is not the case. However, because the energy leaves the waveguide fields from the around and end of the waveguide field, the fields cause the impedance mismatch, which in turn cause the development of the standing wave that distracted. The loss of efficiency various method of impedancy matching for the terminating waveguides is covered in the next section. Alright, waveguide impedancy matching. Waveguide transmission systems are not always perfectly impedance match to their load device. Descending waves the result of the mismatch for the call of the power loss for the reduction of the power handling capability, increase the frequency sensitivity, impedancy change for the device, and therefore in play for the waveguide to match for the waveguide to load those devices or play for the near the source of the waveguides illustrate the device and it's called iris. They are also introduced in inductance and capacitance of the waveguide. Irises are nothing more than a metal plate that contains an opening through the wave to many paths. The iris is located in a transverse plane. The iris show that in this waveguide and the waveguides, the equivalent impedance circuit show the induction, the capacitive, and capacitive inductance wire of iris. The inductive iris is equivalent circle that illustrated in figure 142A. The iris is played with a shunt inductive. The resistance curve of the waveguide is directional proportional with the side of the opening of the node for the edge of the inductive iris, and then perpendicular with the magnetic plate with the shunt capacitor the reacting with an illustrated in the view B. Basically acts the same way, but the acting reacting the directly proportional side of the opening with the edge of the iris is perpendicular with the electrical plane. With the illustrated view C has a portion of curve of the bolt with the magnetic electrical plane forms an equivalent over the LC circuit curve of the waveguide as the resonant resonant frequency, the iris acts as a high shunt resistance. Above and below the resistance, the iris acts as capacitive and inductive reactance. Your posts and screws made of the conductive material can be used with the inductive impedance changing the device waveguide figure 134 A and B illustrate the two basic methods of using posts and screws. The post of the screw, the only partial penetrate the waveguide acts as a shunt capacitive reactance, and when the post or screw extends extremely through the waveguide make contact with the top of the bottom wall to activate the inductive reactance. Note that when the screws are used in and out, the reactance can be varied. Alright, conducting post with the penetrating with the screws. Show that it looks as a capacitive or an inductive conductive passing on post with the screws extending through. Waveguide termination. Electromagnetic energy off the path through the waveguide to transfer the energy stored into the space. The previously mentioned the impedance of the waveguide does not match the impedance of the space without the proper impedance matching, standing the wave of the least of grace. Largest degree of the efficiency of the waveguide and abrupt change of the impedance of the same wave by when the change of the impedance of the end of the waveguide is gradually almost not standing with the form of the gradual change of the impedance. It can be obtained with the terminating of the waveguide and final shape of the horn and such with the three types of illustrated in figure 144, 140A, 4B, 144, 144C. Type of the horn is dependent on the frequency of the disturbed desired radiation pattern. The electrical plan sectorial horn, the waveguide E-plan sectorial horn, the H-plan, the magnetic plane plane sectorial horn, the pyramid horn, waveguide pyramid horns. As you may have known, the horns are really simply antenna. They are simply advantage of their impedance matching device. They serve the large band with a simple construction, and use the horns of the antennas will discuss the further chapter 3. The waveguide may also be determined the resistive lobe of the match of the character of the impedance of the waveguide. The resistive lobe is also often called the dummy lobe. The cover that is only purpose to absorb all the energy of the waveguide without causing standing waves. There's no waveguide to conduct the first termination resistor. Therefore, several special arrangements to either terminate the waveguides. One method to fill the end of the waveguide with a graphite and sand mixture for the illustrated figure 145A. The fills enter with the mixture with the induce the current flow of the mixture, dissipate the energy as heat. Another method, figure 145, show that the heat resistant rod to place within the center of the electrical field. The electrical field causes the current to flow into the rod. The high resistance of the rod dissipate the energy of the power loss. Energy is power loss. And again forms in the heat. So the energy waveguide graphite sand, energy waveguide resistive rod, and also your wedge of the resistive material. 145 termination waveguides. So another method terminating waveguide is with the wedge of the high reflective material shown in figure 145C. With the plane of the wedge is plate for perpendicular with magnetic lines force with the 8 magnetic lines cover the wedge of the current flow with the wedge cover the power loss adds with the other method loss of the form of the heat with the since the very little energy reaching the end of the waveguide reflections are minimum. All of the terminations discussed as far as the design radiated above the energy with the reflection. In many instances, however, all the energies must be reflected at the end of the waveguide. The best way to accomplish the permanently weld the metal plate in the end of the waveguide is shown figure 145D. Alright, waveguide plumbing. Since waveguide is really only one hollow metal tubes insulating with the physical handling of the waveguide's many similarity with the ordinary plumber, they insulate the fact of the ending of the twisting the joint with the insulating waveguides commonly called waveguide plumbing. Naturally, waveguides are different than the design of the pipe, the design with the carrier liquid and other substances. The design of the waveguide determines the frequency of the power level of the electromagnetic energy. It will carry the following paragraph to explain the physical factors of the design of the waveguides. Waveguide size, shape of the dielectrical material of the waveguide must be constant throughout the length of the energy with the move the end of the each of the reflection absorb or abrupt change of the side of the shape of the reflection loss for the overall efficiency. When such a change is necessary, the bend, twisted, and joints of waveguides must maintain the condition to prevent reflections. Waveguides may be bent in several ways that do not cause reflections. One way, the gradual bend is shown figure 146. Gradual bend is known for the electrical bend because it distorts electrical fields. The electrical bend must have the radius greater than 2 wavelengths of the preventing reflections. Gradual bend, 2 times the wavelength radius. Another common bend is the gradual H bend that's called the magnetic bend because it has the magnetic field absorbed the waveguide bent in the manner of the bend. Again, radius of the bend must be greater than 2 wavelengths to prevent reflection. Notice that the magnetic bend, the electric bend bends at dimension more than the magnetic bend is the B dimension normally over the operation. So the 2 wavelengths for the gradual H bend. The sharp bend or either dimension may be either meet the certain requirements. Note if the 45 degree bend of the 148 with the bend of the 1/4 wavelength apart with the reflections of the curve of the 45 degree bends with the cancel each other without leaving the field, but there is no reflection that has occurred. 148, show the sharp at the bend. Sometimes electromagnetic fields can be must be rotated so that they are proper to phase of the load may be accomplished by twisting waveguides shown in figure 149. This must be gradually greater than 2 wavelengths. 149 waveguide twist. The flexible waveguide allows the 150 show the allows the special bend with some of the equipment application made with the required with consider the special wound ribbon. Conductive material must be commonly brass of an inner surface plate of the chromium. The power source of the loss of the greater than flexible waveguide because of the linear surface with the more perfect smooth. Therefore, is only even the short section with no other reasonable solution is available. 150 show the flexible waveguide. Alright, waveguide joint. The entire waveguide system and cannot properly be molded into one piece of the waveguide must be constructed in sections. Sections connected and joined. Each basic type of the waveguide joints are permanent, semi-permanent, and rotating joints. Since the permanent joint with the factory welded joint that requires no maintenance, only the semi-permanent rotating joints will be discussed. Section of the gate waveguide must be taken with a paint with the prepared super permanent joint with called the choke joint, with the most commonly used. The purpose of the choke joint provide with a good electromagnetic community between the section of the waveguide of very little power loss. Cross-sectional view with the choke joint is shown in figure 151A, 151B. The pressure gasket shown between the two metal strips of the form of the airtight seal with the nose of figure 151B with the slot with exactly 1/4 of the wavelength of the A wall waveguide. The slot with the 1/4 wavelength T, but is shown in figure 151A. Because of the shorted at 0.1 at a high impedance result of the 2.2, 0.3 quarter wave from the 0.2. The high impedance for the 0.2 result of the low impedance short of the 0.3. The efficiency it creates good electrical connection between the two sections permits energy to pass with very little reflection of or loss. 151 show the choke joint pressure gasket. Your quarter length wavelength and slot. All right. Whenever the stationary rectangular wave is connected with the rotating antenna of the rotating joint must be U the circular waveguides normally U the rotating joint, and the rotating rectangular waveguide would cover the field pattern distortion. The rotating section of the joint illustrated in figure 152. U the choking joint complete with electrical connection with the stationary selection. Circular waveguide is designed with will operate in the transverse magnetic subscript 01 mode. The rectangular sections are attached with the shown with the illustration to prevent the circular waveguide operating in the wrong mode. Show the 152 show the rotating section, the stationary section, rectangular guide, direction of the propagation of the transverse electric 1 to 0 mode script, and the direction of the propagation of transverse electric script 1 to 0 mode guide, rectangular guide. Distance of O is, this is right here, distance of O is the 3/4 inch high impedance presented with the unwanted mode. This is the most common design with the rotating joint. With the other type of the must be specific application. Waveguides, maintenance, installation, waveguide system present the problems are not normally encountered with the dealing with the other type of the transmission line, but the problems often fall within the technician responsibility, description with the waveguide, handling, installation, maintenance, to help prepare you to maintain responsibility, determine the information, the concern of the waveguide, maintenance of the particular system with the found with the technical manuals for the system. Since the waveguide naturally has the loss of a low loss ratio. Most of the loss of the waveguide system can be caused by other factors and probably connected joint with the design. Damaging or surface is decreased for the efficiency waste from the point that will not work at all. Therefore, you must take the greater care with working with the waveguides to prevent physical damage. Since waveguides are made with the soft conductive material of the copper or aluminum, as you very easily dent or deform, the vent with the slightest damage for the inner surface of the waveguide will cover the standing wave that often internal arcing. Internal arcing causes further damage to the waveguide in action. They often sustaining until the waveguide is damaged beyond you. Part of the job of the technician will be to inspect the waveguide system with the physical damage of the previously mentioned attempts. The only one type of the physical damage can be decreased. The efficiency of the system. Another problem occurs with the waveguide are made with the conductive materials such as the copper. Destructive most of the ships are made of steel. The two dissimilar metals such as the copper and steel are direct contact. Electrical action called electrolysis takes place for the cause of the very rapid corrosion of the metal. Waveguides are completely destroyed by electronic corrosion in the relatively short period of time if they are not insulated direct contact with the other metals. Inspection of the waveguide should be included with detailed inspection of all support points to ensure that the electrolytic corrosion is not taking place. If the waveguide is exposed to the weather, should be painted with all joints sealed. The proper painting result prevents natural corrosion. Seeing the joints prevents moisture from entering the waveguide. Alright, moisture could be one of the worst running with the waveguide system. Previously discovered the related electrical waveguide in the air, which extend with those dielectricals along with the free moisture of the wet air. However, the very poor dielectric can cause serious internal arcing of the waveguide system. For this reason, care is taken to ensure the waveguide system are pressurized and the air is dry. With checking the pressure of moisture for the content of the waveguide air to be one of your daily system maintenance duties. More detailed waveguide installation maintenance information can be found in the technical manuals applying with a particular system. And another guide is the Electrical Installation Maintenance Handbook, AMIB, published from the Navy Sea Command System Command Installation Standards Handbook, AMIB, Navy C 0967LP00000110, volume deals with the waveguide installation maintenance. Waveguide devices. The discussion of waveguide up to this point has been conservative with the transfer and theory 1.2 and another, but many of the waveguide devices have developed, however, they modify the energy and sometimes during the transit, some of the devices do nothing more than change the direction of the energy. Others have the design to change the basic character of the power level of the electromagnetic energy. This section explains the basic operation principle of some of the most common waveguide devices, such as the directional coupler, cavity, resonators, and hybrid junctions. Or directional couplers are the device provide the method of the sampling energy within the waveguide measurement that even in another circuit. That most couplers sample the energy that are traveling in one direction and the other. However, the differential couplers can be constructed with a sample energy of the both directions. They are called bidirectional couplers, are widely in the radar and communication systems. Directional couplers may be constructed in many ways. The coupler illustrated in Figure 153 constructed the enclosed waveguide section, the same dimension waveguide in which the energy is to be sampled the B wall with enclosed with the section of the mount of the B wall waveguide for which the sample will be taken with the two hole of the B wall between the section of the coupler, two hole of the 1/4 wavelength apart. Upper section of the directional coupler has the wedge of the energy absorbing material on the end. The picking up the probe connected to the output jack on the other end of the absorbent material that absorb the energy do not directly to the probe, the proportion of the overall energy through the entire section. Alright, Figure 153 shows the directional coupler, the absorption material, the direction coupler, the pickup probe, the output jack, the 1/4 waveguide, and directional propagation. Figure 154 illustrates the two-portion incidental waveform or wavefront with the waveguide, the wave travel down with the waveguide direction, indicated the effect of the enter of the coupler section with the both holes, both bottom with the portion of the wave travel with the same distance they are in phase. When they arrive at the pickup of the probe, the cover of the waves are in phase. They add together with the sample of the energy traveling down with the waveguide. The sample takes only a small portion energy that traveling down with the waveguide. The magnitude of the sample, however, is proportional to the magnitude of the energy of the waveguide. The absorbent material that is designed with the ensure the ratio between the sample energy and the energy of the waveguide is constant, or the sample will contain no useful information. Incident wave. The incident wave is the directional coupler designed with the same sample of the incident waves. The antenna of the incident wave, the waveguide. Alright, the ratio usually sampled on the coupler informed with the actuation factor. The effect of the directional coupler with the reflected energy illustrated in Figure 155. Note the two waves that do not travel the same distance for the pickup of the probe. The wave represented with the dotted line traveled one half of the wavelength. Further arrived at the 180 degrees out of phase with the wave represented by the solid line because of the wave of the 180 degrees out of phase with the probe. This cancels each other out. No energy to induce in the pickup of the probe with the reflected energy arrived at the absent material and it's added to absorb the material added and cancel out reflected wave. The directional coupler designed the same quarter frequency. The direction coupler designed with the sample of reflected energy shown in Figure 156 absorbed the material of the probe. They were opposite of the position of the direction coupler designed to the sample the incident energy of the position cover the two portions of the reflected energy to arrive at the probe of the phase of the providing sample. The reflected energy sample the transmitted energy, however, they absorbed in the absorbent material reflective wave. The directional coupler designed with the sample of reflected antenna. The simple directional coupler with the sample of both transmitted the reflected energy can be constructed by two directional couplers opposite over the waveguide shown in Figure 157. Absorbent material direction coupler pickup probe output jack 1/4 inch wavelength direction with a proportion and cavity resonators. In ordering electronic equipment, the resonator circuit will consider the coil of the capacitor that are connected in either series the repair with the resonance of the frequency of the circuit and contribute to reduce the capacitance for the inductance for the both. Upon the trees with the inductance of the capacitance for the release, no further the high frequency for the conventional circuit that can be oscillated with the upper limit of the conventional resonance circuit is between 2,300 and 3,000 megahertz. At these frequencies, the inductance amounts consists of the coil of the one half term of the capacity. Many simple straight capacitance of the coil turn one half of the coil is very difficult. Turning the strain of the capacitance even more difficult. In addition, with the circuit will handle with a very small circuit. Small amounts of current. The needs of the module 10 introduction wave propagation explained with 1/4 wavelength sense of the transmission in line with the active the resonant circle the same length of the same of the true with the 1/4 inch section with the waveguide. Since the waveguide is a hollow, it can also be considered the resonant cavity. The definition of resonant cavity is space completely enclosed with a conducting wall that can oscillate the electromagnetic field processing the resonant property of the cavity has been Advantage of the micro-frequency resonant cavity is very high with a merit that can be built with a heavy handle relatively large amounts of power. Cavity for the merit value between 30,000 are not uncommon. The high merit gives the device for the narrow bandwidth, allow for the extra accurate tuning and a simple rugged with a constructing additional advantage. Although cavity resonance is built with a different frequency range, the application variety with the shape of the basic principle operation same for all. One example of the cavity resonating with the rectangular box shown figure 158 with the made by the the section of the rectangular waveguide closed with the box of the end of the conduction plate of the frequency of which resonant mode at 1/2 wavelength distance between the end of the plate of the magnetic and electrical field pattern of the rectangular cavity shown figure 158b. The resonant shape, the A and B, the 1/2 wave with the impedance Z. Magnetic field pattern, electrical field pattern. The 158 shows the rectangular wave of the cavity resonant field pattern for the simple mode. Rectangular cavity is only one of the magnet, many of the cavity device for the heavy frequency resonant 159, 150B, B, C, D, and show the development. The critical cylindrical resonant cavity is infinite number of the quarter wave section of the transmission line of the figure 159 and 1/4 wave of the section should be equivalent resonance with a very small amount of the inductance capacitance 3 1/4 section of the joined with the parallel in figure 159. Both note that all the cutting current carrying about ability with the 1/4 inch section with the greater with any of the other section resonant with the frequency and chamber the curves the additional inductance even the parallel local total inductance but the addance of the capacitance parallel and creep the total capacitance made with the simple proportional thus the resonant frequency remains the same as one of the section. This increases the number of the circuit and the class all the creep the total resonancy increase the merits of the resonant circuit. Figure 5159 show the intermediate step of the development of the cavity 159D show the completed cylindrical resonant cavity diameter 1/2 length resonance frequency. 159 show the development cylindrical resonant cavity quarter wave section equivalent to the LOC circuit and also your quarter wave joints line joints wave lines joined. The cylindrical resonant cavity quarter wave lines joined. Show the figure C there's the cylindrical resonant cavity being formed with the form of the quarter wave sections. The element of the cylindrical resonance with the cylindrical relative cavity being formed with the quarter wave sections, the half wave of the cylindrical resonant cavity. The two variables determine the primary frequency of the resonant cavity. First, for the variable physical side of the general, the smaller side of the higher capacity frequency resonancy, with the second control of the shape of the capacity with the cavity. Figure 160 illustrates the spherical cavity shape that are commonly used. Remember the previously stated definition for the resonant cavities to any complete and closed with conductive surfaces, regardless in shape, can act as a cavity resonator. Cube, cylinder, cylindrical, donut shape, the cylindrical ring, and section of waveguide. Cavity resonators energy of the basically same layer waveguide, similar field with the distribution of the cavity shown figure 161, the energy of the transmitters and electrical mode with the electrical magnet with the reflected back of along the z-axis form the standing waves. These standing waves would form the field configuration for the cavity that would have the satisfied with the same boundary condition than those of the waveguide mode of the operation of the cavity described in the term of the field in the exhibit the x, y, and z. The dimension of the subscript there, the first subscript indicates the number of the 1/2 length along the x half of the second subscript indicates the 1/2 wavelength along the x half of the third subscript indicates the number 1/2 long along the x z length. Energy can be inserted to remove the cavity be the same method that you apply the energy into the output wave of the waveguide of the operating principle, the probes, the loops, and slots of the wear of the cavity waveguide. Therefore, any of the three methods by the injection or remove the energy. Resonant frequency of the cavity can be variably changed with the three parameters: cavity volume, capacity, inductivity. Of the frequency of the cavity is known for the tuning of the method. The mechanical method of tuning may vary for the application. All methods use the same electrical principle. Mechanical method tuning cavity may change the volume of the tuning. Illustrated figure 132, the variable distance of the D will result with a new resistant frequency. The inductance of the capacitance for the cavity charged with a different amount of the volume. The decrease of the resonant frequency. The higher the resonant frequency, the lower the volume of the cavity is larger. The tuning shaft, the disc, and the cavity determining number volume. Or your cavity tuning, the cavity shown in figure 163, the adjustable slug with a screw display along the maximum electrical field with the lines of the electric of the D distance Z represents the distance between the two capacitor plates. After the slug move the distance between the two capacitors because of the smaller of the capacity increase the capacity, because the decrease of the resonant frequency is slug is moved out of the resonant frequency of the cavity, increase the change of the capacity. Method of the changing for resonant frequency of the cavity change of the capacity, the top of the bottom of the magnetic field with the side of the change of the inductancy. Inductive tuning is accomplished with a plate for the non-magnetic level of the air with the magnetic field, the shown figure 163. By changing the magnetic line for reducing the current with the slope with the steps up with the opposite with the H field with the opposite opposing field with the field reduce the magnetic field with the cavity, therefore reduce the total inductancy, reducing of the inductancy, move with the slug and rate of the frequent rate resonant frequency, increase with the resonant inductancy, move with the slot curve lower resonant frequency. Resonant cartridges are widely microwave range. Many of the applications may suit the study of this chapter. For example, most microwave tubes transmit the device cavities, and some of the generated microwave energy of the cavity is determined the frequency of the energy frequency waveguide such conventional measure of the device do not work with the well microwave frequencies. All right, Waveguide Junction. You may have also assumed that energy traveling down the waveguide reach of the junction and simply divide the follow of the junction. Not strictly true. Different type of the junctions affect the energy of the different way. The same waveguide junction usually extend for the most system that you must need to understand the basic operation principle that most commonly use. The T-Junction is most simply with the commonly used wave junction. The T-Junctions are divided into two basic types. The E type of the electrical field, the magnetic type of the hybrids are completely the developments of the basic T-Junction. The magic T and the hybrid ring are two of the most commonly used hybrid junctions. The electric type of the T-Junction, or the electric type of the T-Junction, illustrated in Figure 164, view A is covered the electric E type of the T-Junction, B covered the junction, and arm extends from the main waveguide in the same direction of the electrical field of the waveguide. The Figure 164 of the view B illustrated the cross-sectional view of the E type of the electric type of the T-junction fed into the various arms. The simplicity of the magnetic lines that are also present with the electrical field have been emitted the view K with the input of the field fed into the arm B and output of the taken from the A and C arms. The electrical field arrived at the point between A points 1 and 2. The A1 becomes the positive, the 2 becomes the negative. The positive charges by point 1 into the negative charge on the wall. Point 3 negative charge of point 2 into the positive charge of the point 3. Point 4 with the charge the cover of the field of the code form a 180 degrees with the A with the main waveguide line there for the outputs of 180 degrees output phase of each other in the view of the L with the two-phase input with the amplitude of the area of the A and 2 arms. The single point of the 1 and 2 have the same phase of the amplitude, no difference potential across the entrance of the B arm, and no energy will be coupled out. However, the two signal fed to the A and C arms are 100 degrees out of phase. The shown view M with the points 1 and 2 with the difference potential. The difference with the induced of the electrical field point 1 and 2 with the B arm of the energy is coupled out with this arm. The view and over the views N and P to illustrate the methods of the output, two outputs with only one input. H-type junction. The H-type junction is illustrated in Figure 165A. The H-type junction, the magnetic field type junction, along with the B arm of the parallel plane with the magnetic line force for the magnet waveguide. Again, simply the electrical field shown in the figure on the each axis indicate the electrical field moving away from the observer. The each dot indicate the electrical field moving toward the observer. In view 1, the figure 165B, the signal of the arm B with the in-phase output obtained from the A and C. In view, input signals are fed into arms A and C with the output signals obtained from the B arm we cover the field and junction into the electrical field into the B arm. The 100 degrees out of phase signal are fed into the arms A and C. Is shown the view 3, the no output obtained from the B arm we cover the outputs and canceled at the junction. If the signal is fed into the arm A, they show the UV for the outputs will be attained, and B outputs will be attained from B and C arm. This is also true if the signal is fed into the arm C arm, the outputs will be attained in the A and B arms. H-type junction, E field, high junction. All right, your Magic T hybrid junction. Simplified version of Magic T hybrid is shown with the figure 160 of the Magic T combination of the magnetic and electrical T junction. The most common application of the type of the junction, the mixture section, microwave radar receiver. Operation of the mixer will discuss later in each module. At present, only fields within the Magic T junction will be discussed. So the arm 0, arm A is arm A, arm D, arm C, E plane, arm B. If the signal of the B arm of the Magic T with divided with the two outer phase components, shown in Figure 167A, with the two components will move into the arms into A and C arm. But the signal entering the B arm will not enter the D arm because of the zero potential existing enter the D arm. The potential 0 at this point to satisfy the boundary condition for the B arm. The absence for the potential illustrated in Figure 164B. 167 B and C with the magnitude of the E electrical field with the B arm, and so will indicate the length of the arrow since the electrical fields are in maximum in the center of the B arm and the minimum at the edge of the D arm. Enter the located no potential difference across the mouth of the D arm. Show the input A, D, and output, and then B. The Magic T Magic T input to arm B. The Magic T input to arm B, input and zero potential side view. In summary, when an input of the arm B with the magical T high jump output signal forms the A and C with the 100 degrees out of phase with each other, no output occur with the D arm. This action occurs when the signal is fed by the D arm branch T, illustrated figure 168. There's type of the H magnetic type junction with the signal entering the D arm device with the move down with the AC arm, but the outputs of each other with the input, the shape of the electrical field, and there's motion shown the number of curved slices as the electric field moves them downward to D arm. The points 2 and 3 are at the equal potential. The energy divides equally into the arms, and C, the equal field of the both arms become the identical shape. But since the potential for the both sides of the B arm are equal, no potential difference exists if the entrance of the B arm resulting in no output. When input signal is fed in the arms as shown in figure 169, the portion of the energy is coupled into the B arm, with which for the type of electrical field type T-Junction, equal portion signal is coupled through the D arm, and the action of the H type of the junction, the C arm, and the two fields are out, which either out of phase with each other. Therefore, the field center resulting no output with the C arm. The reverse of the action takes place in the arm. Single of the fed the C arm, resulting outputs for the D arms, no output in the A arm. 169 show the magnetic T input arm A. Unfortunately, when the signal is applied with any arm of the magic T, the flow of the energy output of the area is affected with the reflection. Reflection cover the impact with the mismatch from the add to the junction. Each reflection cover the two major disadvantages of the magic T. Further reflections represent the power loss of the signal, since all the energy fed with the junction does not reach the lobe of the arms fed with the second. The reflection produces the same wave that can result in the internal arcing. Thus, maximum power of the magic T handle is greatly reduced. The reflection can be reduced by using some of the means of dependence matching that does not destroy the shape of the junction. One of the matches shown figure 170 opposed to U with the matches the H plane, and on iris U with the match of the E plane. Even though with the method to produce the reflection, it lowers the power of the handling capability even further. The iris into plane with the match the post of the H plane. The hybrid ring, a typical hybrid ring junction, overcomes the power limitation. Magic T hybrid ring, also called the Brad tray of the hybrid ring, illustrates the figure 171. Actually, modification of the Magic T. The construction of the rectangular waveguide modular molded in circular pattern of the arms joined with the circular waveguide in form E2 for the type electrical field type junction figure 171. B show the wavelength dimension for the hybrid ring to operate properly. All right, I'm going to cut the tape because I just heard lightning. We'll come back, and the next one will be finished up, and then we'll do the summary.